Okay, so now finally, to conclude this chapter, we're going to see an application of entropy. No? So entropy is not just a concept that we define to introduce new notation and make things complicated. Actually, we use it to solve problems. Okay, so the problem that I want to solve is something that we have already seen. I want to know what is the dependence, I want to find the internal energy of an ideal gas. That's what I want to do. Okay, so we know from Joule's experiment that in a single component expansive system, the internal energy in the ideal gas limit is only a function of temperature. But we had established this by looking at the result of the experiment. Now, just because of knowing what entropy is, just having defined entropy, we can prove that. Okay, so the only thing we need to know is what's the equation of state of the ideal gas, and from there we will obtain that internal energy is necessarily only a function of temperature. Okay, so let's see that. Fine, so remember that the first thing you do in every problem is you have to choose your independent variables. Okay, so in this case, independent variables, we're going to choose them to be volume and temperature. You could choose from volume, temperature, and pressure, any two that you like. Okay, so what I'm saying is that the internal energy is going to be written like this, and I want to write differential of internal energy. Okay, so this, by the chain rule, is the partial derivative of u with respect to t at constant volume, differential of t, plus the partial derivative of u with respect to volume at constant t, differential of b. Okay, but also by the first law of thermodynamics, I can write this as dq plus the work. Okay, and if I choose to express these things in terms of reversible quantities, so if I choose to break differential of u into reversible heat and reversible work, and again I emphasize this is a choice that I make, I can write this always as delta q minus pdv. Okay, so this statement, if you like, is completely general, so I'm not saying whether this heat or this work is reversible, but if I write du like that, okay, I'm implicitly saying that the delta q that you see there is reversibly absorbed heat. Okay, if you want to be very careful, you could write it here, reversible, but we don't need that. Okay, so we just know that this heat is reversible. Fine, so from this expression of the first law, I want to get the reversible heat out, and this would be differential of u plus pdv. Okay, now let me write differential of u, which is written up here explicitly. Okay, so delta q is going to be partial derivative, and we already did very similar calculation to this a couple of lectures ago. So this thing, differential of t plus the partial derivative of u with respect to v at constant t, differential of v plus pdv. Okay, so this thing, we can group terms together. Okay, so let's just write that with respect to volume, differential of t plus, and here we put together these other two terms. Okay, so there, and the pressure. Okay, so now let's divide by temperature on both sides. Okay, so let me just write it like this. I will divide by temperature, so I get 1 over t here, and I get also 1 over t there. Okay, so because I made this remark before, so this heat, always keep in mind, because I wrote the work like that, this heat is reversible, and what we have here is the reversibly absorbed heat in an infinitesimal process divided by the system temperature, and this is by the saturated, if you like, generalized Clausius inequality. This is ds. ds equals, in this case, that, because this is reversible. Okay, so we can just write it up here. This is ds, and also s can be expressed as a function of volume and temperature. So generally speaking, yes, I can always write ds as the derivative of s with respect to t at constant volume dt plus the partial derivative of s with respect to volume at constant temperature differential of volume. Okay, and because of this I can identify this term with that, and I can identify this term with that. Okay, so I'm going to just write this explicitly here. The partial derivative of s with respect to t at constant v equals 1 over t partial of u with respect to t constant volume, and this is partial of s with respect to v at constant t is going to be 1 over t partial derivative of u with respect to v at constant t plus the pressure. Okay, so far I'm just pushing you through the calculation. I'm not telling you what I want to do, but essentially what we want, and we know this from the experiment, we know that this thing is zero. Okay, and we want to prove that this thing is zero. Now we have a problem, because if you think of an ideal gas, all we know is the equation of state. So if you like, you can write it like this for, say, n equals 1 mole. Okay, so because we know that, we are able to calculate derivatives such as this, for instance. Okay, things like that, or any other combination of PVT, we can get that from the equation of state. Okay, but we do not know what U looks like. So in particular, we can't evaluate this derivative because we don't know the internal energy. Okay, at least at the moment we don't know it. So we would like to somehow express this derivative, which is, if you like, complicated, in terms of an easy derivative that we know what it is. Okay, and to do that, we are going to use the fact that the entropy is a function of state. Okay, so it's just a function of t and v in this case. So remember that whenever you have a function with continuous derivatives, you can use Schwarz's theorem for the mixed partial derivatives, which is saying that the partial derivative with respect to volume of, in this case, entropy with respect to temperature volume, this thing is just the second derivative of entropy with respect to v and t, and this is equal to the second derivative of entropy with respect to t and v, which is the partial derivative with respect to t of the derivative of entropy with respect to v and t. Okay, so this is the trick. What you have to do is you have to come here and take the derivative with respect to volume, and you have to equate that to the derivative with respect to temperature of this second term. Okay, so let's just do that. So the first thing we have to do is to make the derivative with respect to volume of 1 over t and partial derivative of u with respect to t. Partial derivative of u with respect to t at constant v. Because v and t are independent variables, the 1 over t goes outside, and here I get the second derivative with respect to t with respect to v. Okay, this is the first thing, and the second thing we need is to take the derivative with respect to temperature of 1 over temperature, and here we have pressure and the other derivative, right? So u v t, partial derivative of u with respect to v t. Okay. Okay, so this derivative, we actually have to do it properly. So the first term would be 1 over t squared multiplies p plus the partial derivative of u with respect to v at constant t. Then we write second term like this, the partial derivative of p with respect to t at constant volume, that's this term here, and the final term is 1 over t second derivative of u with respect to v with respect to t. Okay, and we have to set this first line equal to this other thing. Okay, so let's just do it. 1 over t second derivative of u with respect to t and v equals minus 1 over t squared of p plus partial of u with respect to v, t constant, and plus 1 over t partial of p, t, v. And finally 1 over t and second derivative of u with respect to v and with respect to t. Okay, so this is the identity that we arrived to. This thing equals that, because the internal energy also has continuous derivatives and the mixed second derivatives are identical. And remember, what we want is this. Okay, so what we find is that, let me see if everything looks fine. Yes, didn't make any mistakes. So this derivative equals t partial derivative of p with respect to t at v constant minus p. And again, we have achieved what we wanted. This was a complicated derivative. We don't know u, but we do know the relationship between p, t, and v, because that's in the equation of state, and we have transformed a complicated derivative into an easy expression. Okay. Now let me remark, this equation here is completely general. So this is always true, not just for the ideal gas. We haven't assumed at any point the ideal gas. That's what we're going to do now. Okay, so PV is RT for 1 mole, which means that P is RT divided by V, which means that the partial derivative of P with respect to T at V constant is just R divided by B. Yeah, and this is being multiplied by T. So if you multiply by T, this is what you get. And that, you have to subtract the pressure from that. Okay, so you have to subtract the pressure to evaluate this. This minus the pressure is minus RTV. RTV minus RTV is 0. So what we have shown, and we have shown it, we didn't take any experimental result. We proved that simply because entropy exists, the ideal gas has an internal energy that only depends on temperature and not on volume. Okay, so this kind of problem is something that will come up very, very, very frequently in the second part of the subject in advanced thermodynamics. Essentially, all the time we're going to come up with a systematic way of doing this that is always the same. But always there is a situation when there is a complicated partial derivative, and we want to evaluate that. And to evaluate it, we have to look for the appropriate function of state. We can resort to energy, we can resort to entropy, or we can use energy and entropy to make up new functions of state to solve other types of problems. But the procedure is always the same. We want to reduce complicated derivatives to derivatives which are readily evaluated from the equation of state or the knowledge of the coefficients of the system, thermal expansion, isothermal compressibility, and so on. Okay, so this concludes the entropy chapter, and I will see you in the next lecture.